All right, welcome to an MPS Tech Talk. I'm here with Miguel. We're in Barcelona, and we're going to talk about, get into details of fuel gauges today. So, introduce.
I'm Miguel. I'm a battery application engineer. I work here in Barcelona for MPS, and we will talk about batteries today.
All right, great. How about we start with just the top-level battery management system, a BMS, and then we can get into how fuel gauges are part of that system.
Yeah, sure. First of all, the battery management system consists of basically three ICs, we would say. Battery monitor and protector, the main MCU, which share information with the other systems in the e-bike, motorbike, whatever. And then we have the fuel gauge. Every of them communicate to each other in order to make the battery safer and to provide safety to the user, for example.
Okay. And how about the analog interface with the batteries? What's that called, and what is that purpose of that system?
It's called the battery monitor and protector, and it basically takes all the voltage, current, and temperature measurements in order to keep the battery safe.
Okay.
It also controls usually the protections. So, and then it sends all the information to the main MCU, and the main MCU decides what he wants to do. If he wants to send this information for the fuel gauge, if he wants to share this information with other parts of the system, and basically that.
And what's the typical communication protocol between the systems?
It could be I2C, for example, SPI, depending. And for the MCU with the other systems, it uses CAN bus, or maybe, CAN bus usually.
Okay. So do you want to jump into fuel gauge and explain, start with the very basics and why they exist and what's the purpose?
The fuel gauge basically delivers the state of the battery. We usually call it the state of charge, which means the remaining capacity that you have in a battery. This fuel gauge could be embedded in an MCU, or it could be a standalone IC. In our case, we think that having a standalone IC it's better because it comes fully tested. It is way more accurate, and you can save space from your main MCU. So you could reduce cost in the main MCU.
How about we step back and just talk about different methods that can be implemented or have been implemented, let's say, over time for fuel gauge measure state of charge and state of health and those types of things.
There's the famous one, I would say, it's the column counter, which is basically it's an integration of the current through time. So you grab this integrated current measurement, you divide it for the maximum capacity. So you have like a number, and this could be the percentage of capacity that went in or out of the battery. So like if you have this value, you also compute the initial state of charge, so you can know the total state of charge of your battery. It has some downsides. For example, as you are integrating the current, if you have an error in your measurement, you will be integrated this error forever. So that's not good. So a lot of people what try to do is to try to correct this error when you are almost empty or almost full in the battery, like when you are in the boundaries. But in the middle, like in the wide range, you are like blinded. If you have an error, you are not going to see it until you are like in the very end or in the very beginning of the battery. So what people is doing right now is trying to use a mixed model using this column counter, but also using a voltage model based, let's say, which basically uses a cell model to estimate the voltage. So we can do corrections like in every iteration.
So before we get into the the more complex, more advanced systems, so if a column counter is used, so it's like an odometer on your car, right? It where a speedometer might be measuring the current,
Yeah.
and the odometer is measuring mileage, so it's measuring the accumulation of charge or discharge. Can you talk about, maybe more detail, you talked about the issues when implementing it, where you have to re-zero at the full charge or discharge.
Yeah.
What's the problem with doing that? Why does that cause issues?
Yeah, for example, if you don't accurately know the capacity of your battery, because it changes over time and over temperature,
Okay.
you will have like a very, like maybe 5-10% of error in your state of charge.
Just because
right?
over the life of the battery
Yeah.
it degrades over time, or differences between cells just manufacturing, I suppose.
Yeah, all of this in this kind of method, it like results in a poorer state of charge, right? And what does it mean? It means that, for example, if you have a 10% of error, this means that your battery is going to run out maybe before you know it.
Sure.
And this can be translated, for example, in range, as you said.
Right.
Maybe your gauge says, okay, you have 10 kilometers left of battery, right? But it switched off.
Right.
That's going to be awful for the customer, right? And it's not going to be good.
Right. Okay. And then how about if you're, maybe let's say you have a way of recalibrating. It sounded like there's still errors in between as the battery discharges. Can you talk more detail? Why are there errors?
Yeah, because if you are integrating this current and the measurement of the current, of course, from your battery monitor, it's going to be a certain error which is inherent. You are going to have it. You are integrated, so you are deviating for the real state of charge line.
Okay.
And when the system knows, like when you don't know how deviate you are from that curve until you reach
too high
the end.
or too low.
Yeah, you don't know until you reach the end. So at the end you can do corrections, but the battery already switched off. So there's no point on right. The customer is not going to be happy about it.
Right. Okay. All right. And then can you talk the more advanced or the other methods?
Yeah. The other methods would be a voltage method using the OCB, for example. It's a very simple model, but it has like a great downside is that.
Can you just say OCV?
OCB. Yeah, it's a open. It's a open voltage.
Right.
Okay. And this the open circuit voltage is OCB.
Yeah.
So in this method, for example, it's the relaxed voltage. So if you are not charging or discharging the battery, for a long time, the value of the voltage that you're going to be is the open circuit voltage, right?
Okay, open circuit voltage, yeah.
So if you, for example, charge and discharge the battery, you can extract this open circuit voltage.
Right.
So the problem with this is you only can check this open circuit voltage when the battery has been in relaxed mode.
Steady state.
Steady state for a long time. Otherwise, you have to be. You will have an error because the ESR, which is the equivalent series resistance, and because of the dynamics of the battery, until it's not fully relaxed, you are not going to see the open circuit voltage. So this model, it's not, let's say, if you are charging or discharging your battery dynamically, it's not going to be that precise.
And is that just an older technology, or is it like a very simple technology? Is that why it would be currently used?
It's a very simple technology.
Simple. Okay, for maybe applications where the precision isn't as important.
Yeah, I would say. I mean, I think it's not being used that much because if they want a simple model, the column counter it's better than the OCB.
Okay, so that's like the simplest implementation people currently use, probably just a column counter without too much error correction.
Yeah.
Okay.
What some of them, what they're trying to do is the column counter and the OCB method. So they do column counter for the 80% region of the state of charge, and then at the end they apply these OCB corrections.
Okay.
Or they try to apply them.
Okay. So how would they apply them if the battery is discharging and then someone plugs it into a charger right away. Is it possible, or because you're saying it has to be at steady state or rest?
Yeah, they had, for example, if they do a characterization of the cell, they can, for example, you can know the voltage if you are discharging, let's say, a 1.0 Cs, right? You can know the voltage that you are going to have if you are discharging at that point. So some of the customers, they know their current profile, so they can know the voltage drop that they're going to have, so they can apply this OCB, like having the OCB with the voltage drop, and they can correct at the ends of the battery.
Okay. All right, and then how about we talk about the other methods that people are using?
Then we call it the mixed method, the mixed model method, right? Which uses the column counter, but it also uses a voltage method approach. This voltage method approach uses a cell model, a very accurate mathematical cell model, in order to estimate the voltage in each iteration. So we basically use the column counter measurements, this voltage estimation, we combine each other so we can deliver a really accurate state of charge, because we can correct the state of charge in each iteration, right?
Each iteration of each measurement?
Each iteration, we mean with iteration, like every time that you calculate the state of charge, that's an iteration, right? So instead of doing it at the end or doing it when the battery is relaxed, we do it every iteration thanks to using this mixed model. So we don't fully trust the column counter, we don't fully trust the cell, the voltage method, but combining each other, we trust the result of this, because it grabs the better things of each one, like of each model.
And what's a typical cycle rate of the iteration counting?
It depends on the dynamic of your application. It can range from 1 second to 16 seconds. We usually set it at 4 seconds. I think that doing it like less than 1 second, it's not worth, because of course if you do it every 4 seconds instead of 1 second, you are going to save more energy, because all these computational things like require.
And the system probably doesn't change a lot.
No, the dynamics of a battery.
It's a physical system, chemical
system,
right? Okay. For sure. So you're talking about building a mathematical model that the inputs are evaluated against. So can you talk more about mathematical models? Is it like you have one model for all cells, or?
We do a characterization of each cell. So this characterization, we cycle in a certain condition.
When you're saying each cell, you mean like what would be?
Like
so
each
every
model.
Every model, every manufacturer, every one of their models.
Every manufacturer, So we use this every manufacturer or every cell. We do a characterization with specific profile, current, temperature profiles. So we can extract the most important parameters of the cell. This means that we extract the open circuit voltage, we extract the equivalent series resistance, but we also extract the diffusion of the battery, so we can create, of the cell, so we can create a very accurate mathematical model of the cell, right? And we use this mathematical model, we charge it into our IC, so this mathematical model takes the voltage of each cell, the current, and the temperature, and it can estimate what's the voltage in the battery, what's the estimated voltage of the battery.
And you're doing that in a pack, you're doing that on a per cell level?
Yes. Yes, we are doing that, and we think it's very important to look at each individual cell, because in a battery pack, maybe 16 cells, every cell has different voltage, every cell behaves differently, every cell ages differently. So having this individual cell state of charge, individual cell state of health, equivalent series resistance help us to deliver a very, very accurate state of charge. Otherwise, you are going to miss some behavior of the cells.
So if you, what can a customer do with understanding the cell level data? Can they make adjustments or?
Yeah, for example, for the state of health, in fact, if you see that one of the cells is aging very quickly, that means that maybe your battery pack design is not that good. Maybe this cell has more temperature, the connection is not that good, or the cooling system is not working correctly. So having this information really helps for future designs.
Okay.
It also helps to detect if some cells are being damaged. For example, if the equivalent series resistance increases a lot in one cell, that means that, okay, this cell is happening something with this cell, so you should replace it, or you should look at it. And also, it delivers a very good state of charge. Right?
Okay, so you get better measurements. Is there anything that a customer could do with the system that is running with that data? Can they change the way that they're charging, or something to that cell specifically, or?
Yeah, for example, what it's becoming more and more popular is trying to balance your battery using the state of charge of each cell.
Okay.
What does it mean? Well, first of all, what's cell balancing? Cell balancing is when you have, for example, one cell that has more charge than the other cells.
Okay.
You want the battery to be like equalized, the same charge in every cell.
Yep.
Right? So what people used to do is they use voltage, right? So they use the voltage for a balance, for decide which cell has to be balanced. But using the state of charge is a better way to do it because every cell has different capacity, right? So with the state of charge, you ensure that all the cells are at the same state of charge, which does not mean that they are in the same voltage level.
Yeah.
So using the state of charge really gives you more range, for example. It gives you can use the battery longer if you balance using the state of charge rather than using the voltage.
And so when you're doing a cell balancing, does that, are you able to do something, or are they able to do something at a cell level, or does that mean they know that the capacity, like when they're charging, what the actual capacity is on charge and what the capacity is on discharge? If you have one cell that, let's say, is a little bit higher or lower, what can they do?
When, for example, if you are charging, usually you charge using passive balancing when you're charging, which basically you burn capacity for the cell that has the higher capacity, and you try to equalize the pack, right?
Okay.
That's the method. So you equalize this in terms of voltage, but not in terms of state of charge.
Okay.
Right. So doing this using the state of charge would mean that if all the cells has the same state of charge, the battery pack will have like the exact same state of charge, right? You are not, you are charging every cell with the maximum available capacity that it has.
Okay.
But if you do it with the voltage, it may not happen.
Okay, because you might have some cells that have a little bit higher voltage, or so how, when they're doing a cell balancing, let's say you have one battery, one cell that is, let's say it's performing worse than all the other ones. Is there something that can be done to optimize that pack, or are they just stuck with, they have one cell and so the whole pack can only be used up to the capacity of that one cell?
Yeah, for example, if you see this behavior, maybe one cell is like above the in terms of voltage than the other cells.
Right.
So it may reach the over voltage threshold before the other cells.
Okay.
That means that you are not really, like, the battery pack is not really charged.
Because it's limited by the one cell.
It's limited by this one cell.
Right.
So using this balancing, you can put all the cells at the same charge level using the state of charge. So when it reaches the over voltage, all of them will reach at the same time. Like all all the cells will be 100% charged.
Okay.
Right. Which
maybe I'm not understanding a basic thing. So is like the analog front end able to switch off charging to specific cells? So you could charge up the pack. If that one starts to overvolt, then does it just get disengaged, or what's the right way to think of that?
Okay, that's an interesting point, because we enter into the two different kinds of balancing. We have the passive balancing, as I told you, that was you discharge all the cells that are over a certain threshold, but you discharge them. You cannot charge them. You are burning current.
So you're doing on the discharge, you're turning different cells on and off based on the capacity of that cell, the state of charge of that cell. Okay.
Yes. Okay. And then you have the active balancing.
Okay.
The active balancing is a totally different, totally different thing to do.
Okay.
You can basically move, or you can move charge from one cell to another cell.
Okay.
Actively. Okay. So maybe if you are discharging and you see that one cell has less capacity than the other one,
right,
you can pass this capacity to the other cell.
Okay.
Right?
Okay.
So this, for example, is really, really important in a very big battery packs.
Oh, sure.
Because it's very complicated to balance, like passive balance, because passive balancing, you are using a simple resistor for burning capacity, right? But if you do this with 2-3 amps, that's, you are going to need a really big resistance, right? Yeah, because it will blow up otherwise. But with the active balancing, we can achieve 3-4 amps of balancing current, and we are like distributing all the charge of the battery, so we can do it like equalize all the battery actively.
And so is active done on discharge and charge, or?
Yeah, it can be done
in either direction.
Yeah, in passive balancing we don't usually do it in discharge, because you are burning capacity.
Oh yeah,
right?
yeah.
So you don't want to really
put a resistor and heat things up.
Yeah, heat things up, and you lose, let's say,
Okay. So the example of active balancing on charging, if you have let's say one cell that's lower performance, so all the other cells reach full state of charge. Yeah. So state of charge is full, and you have the one cell that maybe is a little bit low.
Yeah.
With active balancing, you can continue to charge that one cell. Is that the right idea?
Yeah. You could send charge to this cell. Yeah.
Okay. And with state of charge known on every cell, with our system, it allows that to
allows that to do it more accurately, because every cell will be fully charged at 100%.
Perfect. Yeah. Okay.
Otherwise, if you don't know the cell individual cell state of charge, you cannot do that.
Right. And you run the risks of, if you don't have accurate measurements, you have to have some kind of threshold below your max, so you don't overshoot, because otherwise you have, you damage everything.
If you do it like the old way, you are losing like some range, right? If you do it with this state of charge method, you will increase the range of your battery, and you will also probably it also ensures like the battery will live longer, because every cell will age at the same time.
Okay. Yeah. So you can correct instead of undercharging everything because you have one bad cell, or overcharge. Well,
it will age more equal.
Okay. How about talk maybe through some fault protection? Does the fuel gauge help in fault protection at all?
It can deliver. Yeah, it could. Actually, it's something that we are trying to push through. As the fuel gauge gives a lot of information, this information can be used as a redundancy in the system in order to provide a second layer protection.
Okay.
As I told you before, for example, the equivalent series resistance, if it increases a lot in one cell, we can know that something bad is happening, right? So we can tell the MCU or the analog front end, the battery monitor and protector, so it can switch off the battery, right?
So like normal fault protection, does it take into account the resistance also, or is it?
I mean, depending the customer, but for example, we say that they should. For example, it gives like, if you have a gauge that gives a lot of information, you should use this information because it's really, really useful.
I get my question was more that information the fuel gauge provides. Is that a unique piece of information that only the fuel? Okay. So the when the resistance is changing in the battery or in the cell, that can be an indication there's some performance issues coming up or occurring.
Yeah, for sure, for sure. And only the field gauge can calculate it. Not all the field gauge does. Only some of them they can perform this calculation. But for example, it also delivers the maximum power available. So this maximum power available is really useful for customers because they can limit their application using this available power, because what you don't want to do is to run out of battery, right, in every situation. So, but you can limit your application. If you are, for example, riding a bike, right? So instead of stopping before you reaches the end, you could reduce the power of the motor using the value of the instant power available. So the customer will have to do more effort, but less than if the battery like runs out of battery.
Okay, so so maximum power available. Is there power available at a certain rate, or
actually, it could be both. It could be instantaneous, or it could be for a period of time. So the field gauge is able to predict using this self-mathematical model that we talked about. It's able to predict what's going to happen if you continue discharging at this rate for example, 10 seconds, 30 seconds, depending on the customer, depending on what customer wants. So they use this, and you can, for example, in your laptop, you can enter into battery safe mode, or you could use like a performance mode, and it helps the customer to define this mode using this like available power for a certain amount of time.
Another topic that's related to the max power available and having the system switching to like lower power state to preserve is around the accuracy of a different system. So there, as you talked about, there are errors that accumulate in errors. Can you talk through like what typical errors are, like just say for a generic system, and how those can be accommodated?
So you mean? I mean, what do you mean in the...
I'm sorry about the measurement error. So like when you're trying to get an accurate state of charge, right? There are, with the different systems, there's all sorts of errors that come back out, right? Or that are delivered. Maybe just talk through.
I think this is a really important topic because a lot of people, they focus on having a battery monitor with a lot of precision, but they may have like a poor field gauging. And if you have what do you want? A very precise battery monitor, but you don't have a good field gauge. At the end, what you want is to have a very accurate state of charge, because that's what you are going to show to the customer. Because for protecting the system, you don't need 1 millivolt of error in the battery monitor, because it's not needed, right? But not all the customers, but some of them, they think that if I have a very accurate battery monitor, I can have a very accurate field gauge, but that's not true. What we say is, okay, you can have an average in accuracy battery monitor, but if you have a really good field gauge, you are going to achieve less than 2.5 state of charge error.
2.5?
Yeah.
What do you mean 2.5?
Your deviation, your maximum deviation from the real state of charge is going to be
2.5%?
2.5%.
2.5%. Okay.
Yeah, 2.5%. So let's say maybe if you have a 5 millivolt battery monitor, and you pair this monitor with our field gauge, for example, you are going to achieve less than 2.5% of error in the state of charge.
Why is it if you have let's say you have an incredibly precise battery monitor,
Yeah.
why would you not get accurate state of charge calculations on the other side, no matter what fuel gauge you use?
If you have a really, really accurate battery meter, you meaning, right?
Yeah.
Yeah.
Well, if it say it, yeah.
You have like a very accurate, but your field gauge is not that like if your field gauge is not accurate, I mean the one that is performing all the calculations,
Right.
is the one that has to be very, very very precise.
Okay.
So even if you are delivering a very good measurements, but your field gauge is not that good, it doesn't matter because the error will be in the field gauge.
So how do you have? It sounds like you can have an accurate state of charge coming out of the fuel gauge, even with, let's say, a less accurate battery monitor. Can you just talk through the math of how?
Yeah.
It seems counterintuitive that could happen.
Yeah, because the way that we are developing our algorithm takes into account the possible errors in the measurements, the cell voltage and current measurements that the battery monitor is providing. So we can compensate this error in our algorithm.
Okay.
So it doesn't really matter if you have 1 millivolts or 5 millivolts in terms of state of charge. It doesn't vary a lot, maybe 1% of error, but having a really accurate battery monitor is maybe 3-4 times more expensive than having a regular one.
Okay.
So that's why we think, okay, if you have a really good accurate, you can like save 4 times the money that you are expending right now.
Okay. So even with say an average battery monitor, you still can get incredibly precise state of charge, which is what in the end,
it's what matters.
What matters, yeah.
It's what really matters to the customer and to the system, because with this, if you don't have this state of charge very accurately, you are going to your customers are not going to be
run out
happy
of power
at all.
or have power when you think you're running out. Yeah. Either way, your phone runs for 1% for hours,
an hour,
which seems really weird, right?
And also, for example, if you go in a car and maybe it says, okay, 80 kilometers of range. Right. Then it goes suddenly to 60, then goes up to 70.
Right.
But that's going to drive you crazy, right?
Right, right.
But if you have one very accurate, it will go very smooth. That's the important thing. It has to be very, very smooth.
Right. Yeah. Yeah. You want to know what the reality of the battery pack is, right? Could you talk through some more of the error? Because it seems like there's a lot more that goes into the system errors or that cause the calculation errors. Like what variations are needing to be compensated for?
For example, the voltage error, the current error in the measurements, because all things electronic things have different errors. So using the way we model our battery in our algorithm, we take into account this error in the voltage and current, and actually in the temperature as well. So we compensate in each iterations the possible error. Let's say our algorithm is it's smart enough to know what is the error. So we compare then the estimated voltage with the real voltage, and we can compensate the error that we are getting to more accurate every iteration. Our algorithm gets more accurate in every iteration because it learns more of the battery as it's going to be.
So every single time it's taking a measurement, it's compensating. It knows there's measurement errors. It knows there are other errors. It knows there's profile changes. It knows there's all of those things. And so it takes into account, how far back does it look back? How many iterations back? Just one?
It learns from one. So you have learned from this one, so you go to the next one. You don't need to it's not that you don't remember the other ones, is that you already updated the important parameters. So actually our algorithm has different learnings. So these learnings changes over time and improve the state, improve the algorithm in each cycle of the battery.
So it's not even it's learning when the product is developed. It's when the product is delivered to the customer and the customer is using the product. There's actual active updating of the algorithm, the parameters, everything.
Yeah, it's self-learning. So it gets better over time. Yeah.
So does it? How about as a battery ages, things change, right?
Yeah.
So how does that get handled?
Yeah. So this is the state of health parameter that everyone knows that it tracks the age, right?
Okay.
So this state of health parameter tells you the degradation of your battery. You also provide this in every individual cell, which I think that nobody is doing this, but as I told you, it's very important because you can know how your battery design is good or is bad, or if you have to redesign it, right?
Okay.
So we use also the equivalent series resistance for helping the state of charge being more accurate, right?
Okay, sure.
Yeah, we use these both because both of them vary, like in time and in temperature, of course.
Right.
So yes, this is cell state of health. Basically, what it's trying to say is the degradation in capacity of your battery from the beginning.
Okay.
Right. So
is that like 100% when it's new, and then it's a percentage of
80, for example.
Total capacity.
Yeah.
Okay, that's state of health.
Yeah.
Okay. Okay. And as you were talking about, the state of health changes over time.
Yeah.
And then also with temperature, there's changes too.
Yeah. The battery, what like we understand and what we know, and that's why we are like developing this complex mathematical cell model, is the battery changes. Like if you change the current, the state of the battery changes. If you change the temperature, it changes as well, right? If you are moving through the voltage, like you are in a very, very different state in like depending on the temperature, the current, and the voltage, right? So we model all the battery in all these, like in all the ranges possible. So with only one mathematical model and using our algorithm, you can do whatever application you want that it's going to be accurate, right? Other people maybe only characterize the cells for one application or for one temperature.
Right.
But if you don't use your system for in this current profile or in this temperature, it's not going to be accurate because the battery changes a lot. Like through temperature, for example, is like changes way too much.
So like let's say a simple implementation, someone does a characterization, they might just do like one profile curve at a certain temperature.
Yeah.
So maybe one temperature, and it's a new battery, and they do the profile so they get one curve, and then they base the whole future measurements on kind of an ideal state.
Yeah.
And so
when you took, like when you, for example, if you do it at 25 degrees, right? This model, but maybe if you are riding an e-bike and it's in the winter, like you are at 10 degrees, right?
Or
winter,
0 degrees. In the summer, same bike, but different times.
And maybe, okay, if you are at 25 degrees, maybe the state of charge is really good, but if you are at 0 degrees, I can assure you that it's not going to be that accurate.
Right.
It's not going to be that accurate.
Right, and so like let's say a less sophisticated fuel gauge would have the one profile, they'd have to optimize it somehow to deal with the temperature. But is it, I'm just thinking through the model we have. So we're characterizing to deal with age, temperature, what other concepts that?
Using this, using the model, in our algorithm, we can also calculate the runtime, like the time to full, the time to empty. We also can know the fast charge time, right? And all these, like the available maximum power. We also have this is also really important. from our characterization, we also extract a thermal model of the battery that we implement, that it's implemented in our algorithm. So we can predict at what temperature your battery pack is going to reach the end.
Okay.
Right?
Okay.
So why is that? Because the battery, like the internal states of the battery changes a lot with temperature. So, but if you start at 0 degrees, because the environment is at 0 degrees, as you start discharging or charging, your battery is going to self-heat itself, right? So the end point maybe is 20 degrees.
Right.
Right?
Yep.
But if you don't have this thermal model that can predict what's going to be the end point, you may calculate the shock for 0 degrees.
Right.
But you are really at 20 degrees.
Right.
So
Yeah.
you are going to be a really huge error,
Right.
because the state of charge at 20 degrees is very different than at 0 degrees. So with this thermal model, we can more accurate deliver a good state of charge. And this is something that we also extract from the characterization.
Yeah, so we have the model that is a mathematical representation of the battery throughout all of the different range of operation.
Yeah, range of operation.
And so you can have the algorithm adjust based on, it's a mathematical with actual data input, and then it can, if we've never run the characterization of the battery in that actual situation, the model though can predict and much more accurately than just fitting to a curve of one characterization.
Yeah.
So I think you're talking about one of the challenges of the current technology is the simple characterizations, where a characterization might have been done in a certain parameter for a certain application, and then that characterization could be applied, or people say, well, here's our characterization, use this, and it may or may not be appropriate.
Yeah, we have seen that. We have seen that maybe they do 5 different characterizations for the same cell model.
Okay.
Because they do this characterization in different, in different current profiles, different temperatures, but you can only charge one of these profiles in your field gates.
Right.
Right.
Yeah.
So if you do that, if you want to, if your application changes, you will have to be changing the model, finding the good one for your application. It will come with a lot of tests.
You have to compromise
everything.
Yeah.
What we say, okay, we deliver a very accurate cell model which fits every application.
Right.
It doesn't matter what's the application. If it's highly dynamic, high current, low current, whatever, high temperature, low temperature, it will fit every of them. So you don't have to care about it. And we do this. We talk with the customer. We say, okay, what's your cell model? It's this one. If we can, we purchase it, or maybe they send us. We do the characterization, and we extract the cell model, and it's uploaded in our standalone IC.
Right. So it's like a really high level calibration of the model.
Yeah.
So you don't have to do it for every single other application. You do one.
Yeah, sure. And also we don't need calibration.
Okay.
It's not needed inline calibration. It's not needed any.
Well, can you talk
cycle.
about what's the? So we don't have calibration. So how else would it be done? With another type of solution.
Some of them we know that you have to do a learning cycle to know the capacity of the cell. As we have talked, the column counter relies on the capacity value to calculate the state of charge, right? So they need a learning cycle to know the exact capacity of your battery.
Okay.
But as we do this mixed model, from the characterization, we already know the capacity of the cell.
So what do you mean? Can you just talk through what is a learning calibration?
Yeah, it varies depending on the competitor, but it usually takes 2 or 3 days. You basically do 0.2 or 0.5 C rate charge and discharge with very long relaxing time.
Okay.
So the IC can know the exact capacity, it can know the open circuit voltage, right? But you need to do like all these steps for 3 days or 2 days. And for the customer ends, it's not that easy to do it because maybe you don't have the equipment, right? To do it. You don't have to have like temperature chamber, electric
so you have to
load.
control all of that.
Yeah.
Okay.
It's not
And so,
efficient.
so for a customer using that type of solution, they would have to take their a production pack, for example, and then they have to do this calibration sequence.
Yeah.
And then that calibration sequence would be good for as long as nothing changes over, all the production. So if the cells don't change, or if the, anything, like if they even change like something with the way the configuration of the pack or something.
If it changes, you will have to do
You'd
the learning cycle.
You'd have to do relearning. And with our solution, what do you do for your calibration when a customer starts up production?
They don't need to do anything, actually. I mean, as we characterize the cell, we already know the capacity. This cell model, it's loaded in their IC. And the only thing that they have to do is basic configuration. They need to say what's their battery pack configuration, if it's 10 series cells, 15 series cells, whatever parallel cells they have. And usually what we also ask is, okay, can you tell us what's the current that you are going to charge, what's the average current that you are going to discharge. But then while the pack is cycling, we have these learnings that can know at what current are you charging your application, what average current are you discharging. So we only ask the most important parameters are the battery configuration, the voltage, the maximum voltage, the minimum voltage, and the charge voltage. And with all of this, it can run very accurately. Of course, if you know more and you want to tweak more parameters, like you can do it also.
Okay, so you can do like, let's say you want to be really precise, and you could do some kind of validation, calibration, or something.
Yeah, if you want to if you want something very easy, you can just
plug it in
as
and
I
it
said.
works. Yeah.
But if you want like way more accurate, you want to tweak some parameters, it can be possible. I mean, we have 2 different modes. Let's say the standard mode, which has maybe 5, 10 parameters that you can change, and then we have the expert mode that gives you the allowance to change more and more parameters.
Okay.
And we offer this guidance. You can ask us if, I want to change this, how this could be changed, and we do this assistance to them.
Okay, great. The technology of doing this mixed mode, what has changed over time that allows allows us to implement this mixed mode? Why is it something that hasn't been done previously?
I would say it requires a lot of expertise. It's not easy to implement it, and it's really hard to validate it. So what we usually, when we talk with customers that they maybe develop their own algorithm, it's very difficult to validate a state-of-charge algorithm for every application, for every temperature, every current. You have to do a lot of tests, and it's really complex. Also, if you are doing this in your MCU will require a lot of computational power to deliver a good state of charge, because you are running other things. You are running the communications. You are talking with the battery monitor and protector. So if you are adding a very complex model as the mixed model could be, maybe you don't have enough space in the MCU.
Okay.
And also because 10 years ago, you only had 3 LIDs showing your state of charge, right? Or 4 LIDs. So if you had a 25% of error, that's okay. You are not going to see it. But right now, some phones, maybe they have, they say 25.3 state of charge. So if you don't have that accuracy, it's not going to be good, right? So that's why we need more and more accurate models, because because of the customer experience. Because we are now showing at least every application, like e-bikes, mobile phones, motorbikes, they have at least 1% of error, like state of charge that they are showing.
That they're showing,
right?
Yeah.
So that's why we need a really accurate, and because we thought that the column counter wasn't enough for delivering these high-end solutions.
Good. Is there anything else that that we should cover that you?
I think we have covered the individual cell state of charge, health, current resistance. I think that's one of the strongest points. The available power, which is really, really interesting for power tools, for e-bikes, for motorbikes. It's a really important parameter. And regarding the battery monitor and protector, we already said that customers, they don't really, you can focus on the accuracy of the voltage readings, but if you have a very, very good field gauge. If you don't have a very, very good field gauge, it doesn't matter, and you're spending a lot of money in this.
Yeah.
And let me add something on the battery monitor and protector, because it's really interesting, the parts that we have, because they can also save a lot of money in with using our part, because we have a highly integrated IC with the high side driver for the MOSFETs inside, and also because we have this soft start capability feature, which basically means that you can avoid the pre-charge circuitry, because we control the gate of the MOSFET, right? For turning on these MOSFETs, we slowly increase the voltage of the gate, so the MOSFET allows a small current go through it, a control current, so it can charge the load, right? And we are doing this with the IC with any extra circuitry, so we estimated $0.6 for each battery pack that you can save using our IC, because we don't need this pre-charge circuitry. We are doing this soft start control, and I think it's very interesting. It's very interesting. Sorry.
And what is so it's a soft start, so you don't have to have circuit protection on over a spike on.
Yeah. So what happens if you switch on the battery? If you connect the battery to a load, the load is 0 volts, right? The battery is 28 volts. If you switch on the MOSFET, the current is going to be a very huge.
Right.
So
what's the current way that's handled?
Yeah, they need an extra pre-charge, what it's called a pre-charge circuitry, which it's basically a MOSFET with big resistor, big in terms of it can dissipate a lot of energy.
Okay.
So you close this MOSFET, and with using this, you have a MOSFET and a series resistant. So you close this MOSFET, and the current is sinking through the load.
Okay.
Right.
And
so
it
it's slowly,
ramps up.
it ramps up. It's slowly increasing the voltage in the side of the load.
Okay.
But you need this configuration. You need the resistance, and you need the FET.
Right.
And the protections of the FET and everything.
Yeah.
So with our solution, you can avoid this. You don't need it. Why? Because we are ramping the voltage of the gate.
Right.
The way that the MOSFET is slowly closing, allowing a small current go through it, and slowly increasing the voltage of the load. So when the load achieves the correct voltage, we turn on. We close the MOSFET completely.
So it emulates a resistor MOSFET with actual just step up of.
Yes.
Okay.
Yes.
Very neat.
Yeah. And this is a feature, a unique feature that we have. I think no one is doing this.
Okay. Very cool.
That's really, really good for us.
Yeah, that's great.
Yeah.
Okay. I think we covered a lot of things. Hopefully, people become educated on fuel gauges and different solutions. But thanks for your time. It was great talking with you.
Yeah. Thank you to you. I hope they understood a little bit better what's a field gauge and why they need it. So I'm happy to help.
All right. Excellent.
Okay.
All right. All good.